Hello friends, the title of today's talk is Combinatorics, the art of counting. To start with a simple example, suppose there are three places A, B and C. There are three different routes to go from A to B. There are two different routes to go from B to C. So the question is, how many different routes are there to go from A to C? Well, as it is easy to calculate or to enumerate, the answer is 6, which is 3 into 2, because for each route from A to B, there are two routes to go from B to C. So for each route from A to B, there are two routes from go from A to C. So 3 into 2, the answer is 6. So we can generalize it. Let there be three places A, B and C. There are m different routes to go from A to B. There are n different routes to go from B to C. So again the question is, how many different routes are there to go from A to C? And the answer is m multiplied by n. So this is the basic step of combinatorics, the art of counting. Without counting the number of, without enumerating the complete set of routes, we are just counting the total, which is m multiplied by n, as the number of routes from go from A to C. So now let's go to a bit more complicated problem. Consider three integers 3, 5 and 8. Question is, how many three-digit numbers can be found arranging the digits 3, 5 and 8? So we can always enumerate them: 3, 5, 8, 3, 8, 5, 5, 3, 8, 5, 8, 3, 8, 3, 5, 8, 5, 3. So the number is 6. So the answer is 6. Now we go to a bit more complicated one. So there are 5 different numbers now: 3, 5, 4, 7, 9. And the question is, how many 5-digit numbers can be found arranging the above 5 digits? The answer is 120. It is hard to list down all the arrangements and count the number to be 120. So we need to produce a list of 120 numbers to enumerate them and then get the answer. But there is a tricky way to bypass the enumeration. We need a counting technique. So the technique is, start with those 5 numbers 3, 5, 4, 7, 9. Start with 5 positions, 5 vacant positions: 1, 2, 3, 4 and 5. The number of ways these 5 vacant positions can be filled by these 5 digits will give me the answer. So I need to fill each position with one of these numbers, and one number can be used only once only. So the total number of arrangements will give me the number of digits that can be found using these 5 digits. So how to count the number of arrangements? So we start with 5 digits, 5 positions, and the total number of ways we are counting like this. The first position can be filled up in 5 ways. I can put any of 3, 5, 4, 7, 9 in this position. So for the first position, there are 5 choices. Now once one is put there, one number is kept in the first position, there remains 4 numbers for the second position. So the second position can be filled up in 4 ways. Now once I put 2 numbers in first 2 positions, there remains 3 numbers left. So any of them can come in the third position. So for the position 3, there are 3 choices. Similarly for position 4, there are 2 choices. And once I keep 4 numbers in first 4 positions, there remains only 1 position and 1 number. So the last position can be filled up in only 1 way. So following the similar argument as before, the total number of arrangements will be 5 into 4 into 3 into 2 into 1, which is 120. So we have got a simple counting technique giving me the answer without completely enumerating the number of arrangements. First position can be filled up in 5 ways, second position can be filled up in 4 ways, so together can be filled up in 5 into 4 ways. Third position can be filled up in 3 ways, so 5 into 4 into 3 is the number of ways first 3 positions can be filled up, and so on. So the answer is 120, which we sometimes call 5 factorial. So the general problem is, so there are n objects a1, a2, an, and there are n positions p1, p2, pn. So how many ways n objects can be arranged among themselves? That is the number of ways these n positions can be filled up by these n objects. So if we count the number of ways, first position can be filled up in n ways, and once first position is filled, one object is gone. So the second position can be filled up in n minus 1 way. Similarly, the last position can be filled up in 1 way. The last remaining object, with the last remaining object. So the total number of arrangements is n into n minus 1 into n minus 2 up to 1, which is n factorial, which we call n factorial. Now let us consider this problem. There are 4 numbers, 3, 5, 4, 7. How many 2-digit numbers can be formed arranging the above 4 digits? So we have 4 objects now. Okay, we can enumerate the complete list: 3, 5, 3, 4, 3, 7, 5, 3, 5, 4, 5, 7, 4, 3, 4, 5, 4, 7, 7, 3, 7, 5, 7, 4, and the answer is 12. So the answer is 12. But we can avoid this type of creating exhaustive lists, and we can use let us apply our newly learned counting technique. So we have 4 digits. We have 2 positions now. We need to form two digit numbers. So there are 2 positions, and the number of ways for the first position, it can be filled up in any of these numbers. So number of choices for the first position is 4, and once I put the first number, there remains 3 numbers which can be used to fill up the second position. So for using 3 numbers, second position can be filled up in 3 ways. So the answer is 4 into 3 equal to 12. So we have got the correct answer without complete enumeration. So this is the art of counting, which we call combinatorics. So in generalization, we have n objects, a1, a2 up to an. In how many ways above n objects can be arranged among themselves taking r, where r is less than n, less than equal to n objects at a time? We call this number NPR, n permutation r. We studied these terms in the schools, so we call them NPR. We call the number NPR. So how to find the number? So there are n objects and r positions, P1, P2, PR. And the number of ways is, for the first position there are n choices, for the second position there are n minus 1 choices, and for the rth position we have n minus r plus 1 choices. So the number of ways is n into n minus 1 into n minus 2 up to n minus r plus 1, which is n factorial, by n minus r factorial, which we call NPR. Now the second question is, in how many ways the above n objects can be grouped among themselves taking r less than equal to n objects at a time. Now previously we were considering the order, but here we are not considering the order, we just need to group them. And we call this number NCR, n choose r. How many ways n objects can be grouped in r positions? Consider NCR groups of n objects taking r at a time. So let there be some number NCR, which is the number of groups of n objects taking r at a time. Each group contains r objects that can be arranged among themselves in r factorial ways, which we learned before. So we can state the relation NPR equal to r factorial times NCR. So that gives me a formula for NCR. So we get NCR equal to NPR by R factorial, which is N factorial by R factorial into N minus R factorial. There are some identities which we can either argument it out or can use these formulas to see the identities. One is NCR equal to NCN minus R, where when we are forming groups of R, the groups of the remaining objects of number N minus R is forming another group. So those two groups of number are same in number. So NCR equal to NCN minus R. Then NCR equal to N minus 1 CR plus N minus 1 CR minus 1. N minus 1 CR are the number of groups taken R at a time, excluding a particular object. And N minus 1 CR minus 1 is the number of groups taking R at a time, always including that object. So the total number equals, total number of those two groups equals NCR. Suppose there are 5 objects where there are 3 objects which are identical. In how many ways the above 5 objects can be arranged among themselves taking all at a time? Where we are arranging them taking all at a time, but 3 of them are same. Let the answer be X. Sorry for a bit distraction. So had all 5 objects been different, the total number of arrangements would have been 5 factorial, which is 120, but 3 of them are same. Had all 5 objects been different, each of the X arrangements, which we considered the number of final number of arrangements, would have produced 3 factorial equal to 6 arrangements. So we get the identity 3 factorial times X equal to 5 factorial. So we get X equal to 5 factorial by 3 factorial, which is 120 by 6 equal to 20. So number of arrangements of, let me see if it is here. Okay. So the number of arrangements of n things where R are same is N factorial by R factorial. And there can be several groups of such objects, R1, R2. So it will be N factorial by R1 factorial into R2 factorial into up to Rk factorial. So now let's go to the last problem. Consider a 2 by 2 grid here. I have 2 corners A and B. One needs to travel from A to B along the lines. One can move only rightwards and upwards. Question is, how many such routes are there? So first, let us consider the complete enumeration. One route is right, up, up. So that is one route. Then another route is right, up, up. Third route is right, up, right. Fourth route is up, right. Fifth route is up, right, up. And the sixth route, the final route is up, right. So the answer is 6. Now how we can get the answer without going through the complete enumeration? So each route is an arrangement of R, U. So there are 4 objects, 2 are same and another 2 are same. So the number of arrangements of R, U is 4 factorial by 2 factorial into 2 factorial, which is 6. So we can generalize this problem. Consider an M by N grid. Suppose one needs to travel from the bottom left hand corner to top right hand corner following the lines. And obviously one can move only rightwards and upwards. So how many different routes are there? The answer is M plus N factorial by M factorial into N factorial. So you can always discuss this problem with your friends with particular values of M and N, and you know the answer.